Hello, glad to be back. Been a while, hasn't it? How long's it been? Yeah, so how long's it been since I was last on here? I can't even think when it was. Well, that's good, isn't it? I know that YouTube have changed the way you can do your Hangouts now, so you can't actually go live, can you, unless you've got OBS installed and this, that, and the other. Yeah, and what you can do as well. I mean, when you do put the actual video out, and we can all join in and we can be in the chat as well while the video is playing, can't you? You know, as a premiere. So yes, it must be well over 3 years. Well over. Yeah, something popped up on Facebook actually for like 3 years ago, or 2 years ago, from when we was talking about doing the UK convention. Remember when it first kicked off with Gary John the first time? Well, I think it was 3 years ago on Facebook. Like, yes, I've been blocked a few times. I only shared that Carl Froch post into 4 groups, and they banned me for sharing into groups. And the best thing about it were 3 of them were my own groups. So you know what I mean? There is a lot of censorship now. What they do, they give they give you the option now. When you share to a group, before you used to have to do it individually, share to the group, then come back out, go back in and share it to the next group. Now they give the option just to click down on the groups, yeah? So if you've got a list of groups and you just share, you click about 5 of them and they call it spam and then they block you. They've made it easy to share into groups, but they restrict you a lot quicker now. Because before, I've never been blocked or anything for sharing into groups. And I've shared stuff into like 100 groups in one sitting, you know what I mean? Now you share into 5 or 6 groups and they block you. Exactly, that's what I'm doing. And like I say, the first 3 groups I shared into were the groups I'm admin of. So, you know what I mean? So it's a load of rubbish. Yeah, sharing moon and sun and moon readings on Sun and Moon group. Yeah, well, we had thousands and thousands at one time, didn't we? Yes, it's been a quite a interesting journey. You know what I mean? I've been through ups and downs. I'm now a single man living in a little flat. You know what I mean? A lot of stuff's happened.
I was merrily talking away there and realised that I didn't have my microphone on anyway. My microphone's on now. So we were saying we met on Facebook and and moon readings, and I was saying that we've watched you evolve.
Yeah, and it's been an interesting journey. Like I say, it's obviously when I first found out about flat Earth. Obviously, I had a family, had my own house and all that, and now I'm a single guy living in a porky little flats in the middle of nowhere. So yeah, things change. You know what I mean? But like I say, I've done quite a lot this year. I've been to New Zealand, did a presentation, went to the UK convention. Yeah.
Anyway, yes, you're hot. You're hot from the UK convention, aren't you?
Yes, I've just come back from the UK convention. I couldn't get there on the Friday, but I got there on the Saturday morning, and it was great. You know what I mean? Obviously meeting a lot of regulars, but obviously meeting new people. Paul on the plane were there. Mark Sargent was there. My highlight was meeting Mark Devlin. I don't know if you know Mark Devlin. Does all the conspiracy in regards to the music industry, but he is a great guy to look up on, and he does amazing stuff on the Beatles, and particularly Paul McCartney. Obviously, he apparently died in 1966, and he was replaced with somebody else. So I definitely look into Mark Devlin, and I had a good chat with him. And yeah, it was a good. And like I said, the presentation went down a storm because what I did, I produced a presentation what a lot of people didn't know a lot of stuff about. You know what I mean? Not many people know much about the moon. Well, we do, but we don't know about it from a flat Earth perspective or a global eye perspective. And what I tried to do, I tried to present my research from a flat Earth perspective. You know what I mean? Like what I did, I showed a load of proofs that we don't live on a spinning ball, and then it says, right, now that you understand that we don't live on a spinning ball because of this, this, and this, let's look at the moon from a different perspective. And that's what the presentation was about. And maybe we can go through some of the presentation.
Yeah, that's why you've come to join us for this bit, isn't it? Is to go through some of your presentation.
Yeah, so the reason why I didn't show my icon is because when you share the screen, sometimes it lags a little bit, and I didn't want it to lag. That was all. So yeah, but it was a great time at the convention. Obviously, I met Robin for the first time. Obviously, knew Roxanne. Ruben was there with his family, and like I said, just got to meet a load of new people. a guy called Rob Mackenzie who I met from up the north a little bit near Newcastle. Yeah, so like I said, meeting new people and getting the opportunity to do my presentation, it was brilliant. I really enjoyed it, and it was nice to put the presentation out and try and show some people. You know what I mean? I didn't get too technical. I tried to keep it quite so people could understand the presentation, because when you're doing a lot of measurements and you're measuring the speed of the moon, you have to get quite technical, and it you know what I mean, it can confuse me sometimes when you're trying to explain things, because these things aren't that easy to explain, if you know what I mean. So yeah, I tried to keep it quite basic and just go through the basics and show what I've done over the last 3 years in regards to, I've done the laser experiment with Dr. John D, and I've made quite a few observations. I've been measuring the actual disk of the moon when it's been full, to show that there is a change in size, which we'll go into as well. Because one of the questions what I got asked quite a while back was, well, if the moon is closer in the flat Earth model, why isn't there a difference or a change in size? And so I thought, well, what we'll do, we'll measure it then. And what I found is, when the moon is on the horizon, it's smaller, and as it rises to zenith, it gets bigger. Now, in the globe model, that would be impossible at certain times, because they have what you call apogee and perigee, like a closest point and a furthest point. On one of my observations, the moon, according to the globe model, is actually several hundred miles further away from when it rised to when it was at zenith. You know what I mean? But it actually got bigger, which is completely debunk the globe model. And what you'll see with my measurements are, they're very, very accurate. And what I did recently, I don't know if anybody saw the European convention, but Paul on the plane asked me to measure some globe images, what he got from that. Is it the Himawari 7 satellite or whatever? I can't remember which one it were, but it was one of these satellites, what's supposed to be a million miles out or something. And what we found were that every single image was the same size. So what it showed is that my measurements were accurate as well. Even, you know what I mean? So it's like I say, it's a good talking point, and it puts a lot of questions out there, because like I say, there is a lot of questions in the distance of the moon.
It's very strange sometimes, Dave, when you look at it and people capture it with numbers on it and faces on it and all these other things on it. It's like, this looks like a very wonky patchwork up there.
This is a question what I'll ask in the presentation, you know what I mean? Sometimes it looks like a disc, sometimes it looks like a ball, sometimes it looks like it emits, but we'll get to that in a bit, because like I said, the moon, it can be so many things, we just don't know what it is. It's been there every night for...
And also, Dave, I thought, when Enoch, I thought, oh, not another great book and all this kind of stuff, but didn't poo-poo it, but I just like, anyway, I agree with Enoch now. I've seen the moon just appear outside my house, literally come out, just as if it wasn't there, and then someone turned a light on. But it comes out it takes about a few minutes to appear properly, so a bit of it comes out, as if someone's opening the curtains and it's coming through. I've seen it myself, and there was one time, or a couple of times, I've gone to like the garage with my daughter, and the sky's clear and the moon's not there, and when we come back, the moon's there.
I've upgraded my camera. I don't know if you can just see behind me now. I've got the new Nikon Coolpix P1000. So I've been updating a lot of my older observations, what I shot on my older camera. So that's another journey in itself, just replacing all my old observations. Because what I did with my previous camera, the software I was using, which I have to pay for, I only had the free version of it. So I could only make my observations at a certain resolution. So what I've started doing now, I've started reshooting my observations and updating them and updating the resolution. So I'm now getting the full resolution with more accurate results as well. So that's been a journey in itself as well. But I'm slowly getting through my observations. You know what I mean? Like, I don't know if you see my last one where I measured the moon at apogee and perigee to show there was a change in size.
Can I ask you something as you're here on that? A lot of people capture the moon and the sun with a rim round it. Now, someone said to me that they thought that was because they were out of focus, but a lot of people capture it when they feel they're in complete focus that it's, you know, there's a rim around it. You can see a line going around it. Both of them.
Well, what I've noticed is when you get a full moon, you do get like a funny little ring around the moon. But I think it's just the software, the imaging software. You know, what produces the actual image. Because what I notice is when I take like a 4K snapshot and I edit it down to like a single frame image, I got that weird like ring around it, like you say, it's got that ring around it. But when you take a single frame shot at you know what I mean, a close-up shot, you can't see it in the normal image. So I think it's just the image processing. But like I say, you do get that little ring around it, especially when the moon's full as well.
And also, obviously, Wide Awake, he was filming the sun. The sun was, you know, it doesn't go into the water, but you know what happens when it hits the water. You captured the nice green poof as it disappeared. You can see through the sun. Actually, at that point, he's filming and you can see through it.
Yeah, well, you're looking at the moon through a lot of layers of atmosphere as well, you know what I mean? So
yeah, I remember. I remember.
Well, they're both celestial objects, aren't they? But I personally think they're two separate objects. Yeah, I've captured the green puff as well. Yeah, I went. Yeah, I went to Brighton, and I said to Dr. John D, I says, is that sun going to set over the ocean? He says, no, it sets over land over there. And I looked at the sun and I thought, there's no way that sun is going to set over land. Yeah, it was only like a few degrees off the water already, and I thought, there's no, you know what I mean, it's going to set over the water. So I got my camera ready, and funny enough, it set over the water, and as I filmed it, it just disappeared into like a green puff of smoke. It was brilliant, and it was good to capture it as well. Yeah, well, I've got a farm at the end of my garden. I live on like back of a field, and there's a house. It's probably 10 miles away, and I can just about zoom in on that house. You know what I mean? I can get the house in frame like it. So yeah, the cameras can't really zoom very far, but obviously when you're looking at celestial objects, especially things like Polaris, which is God knows how many trillion miles away, and it's in perfect focus, and it's in the exact same focal range as the moon as well, because all the celestial objects are at the same focal point. Yeah, people say, yeah, they're at infinity. No, they're not. The camera isn't set to infinity. If you want to shoot Jupiter's bands or Jupiter's moons or Saturn's rings, yeah, you need to focus your camera, yeah, and if you focus it to infinity, it'll just be a brown blob. So what I've done previously, when the moon's been out, I've actually gone into manual focus, focused the moon craters really clear, locked the focus, then switched it over to Jupiter or Saturn and shot them in perfect focus. Well, it's got it's got a mode on it called infinity mode when you're shooting far away objects, like. But whenever you're shooting celestial objects, you can't. They're not in focus in infinity mode. You have to focus it, and it's like I say, it's not in the infinity mode. You have to go into manual focus, and the bar is not. You know, you got the focusing bar. It's not fully to the top. Infinity is at the top, and it's nowhere near the top. You know what I mean? It's quite a little bit off. Good thing about the P1000, you've got a focus ring on it as well, so you can like do very, very fine adjustments on the focus, which is really good, which I really love. But I do love the camera, and it's so much better than the B700. I didn't think it was going to be that better, but it's not only a better camera as such, but the actual use of it, you know what I mean? It's got manual moving mode, so you can shoot something in manual moving mode, and you can change the settings while you're recording as well. And what I found is you can learn how to use the camera a lot better, because when you're focusing or changing ISO settings or aperture settings in manual mode, then you can change them over onto the actual camera mode and use them similar settings when you're shooting it in single shots. Yeah, definitely. I mean, it's still got a shitty sensor in it. You know what I mean? So
it does more what you want it to do. I really wish we knew what we lived on. You know, the other day we had a hangout with Charlie Freak, and he's on Mexico City time, and that's 5 hours away. And he's down there in South America, Mexico. Mexico might not be quite south, but he's that far away, and yet he's only 5 hours away, like New York. So it's obvious that the land twists round. I'm pretty sure the UK lies on its side. And then on your phone, you can actually twist the continents around. And I think because you can do that, if you twist everything, that's the shape we are. I don't think we're anyway the way that they say.
I think at one time when we changed the clocks back, there's only a 3 hour difference between us and Brazil. It's mad. Yeah, yeah, because we change our clocks back, but they don't change theirs back like for a few months. The same in America. We change ours back. I can't remember. Is it end of October or November? And they change theirs the following week. Like,
Yeah, but we can't do it all. We're the people. We work. They've already got us as slaves, already in the slave system. And then what you're doing, other people like you're being like scientists without any help.
yeah, same with Future Ventura. Future Ventura is like west of the UK on the longitudinal line, but it's the same time zone. Because when I got there, I was like,
But if you twisted the land round, like I told you, and England's lying on its side, and you twist it around, then it all lines up.
yeah, exactly. You know what I mean? I'm just making observations and just documenting it. And like I say, I've got so many folders on my computer now with different observations in, and I've been building them up. You know what I mean? So I've got a good collection of like the moon at zenith, the moon at apogee, the moon at perigee. Yeah, I've got loads and loads of different folders. In fact, what I'll do, I'll just share the screen and I'll just give you an example. Yeah, because what I did at the beginning of my presentation. Yeah, there's a lot of myths going around in regards to flat Earth. You know what I mean? The moon rotation's a myth in itself. Like I say, there is some things in the moon rotation I don't understand myself. You know what I mean? I put my hands up and say, you know what I mean? But I have been looking at the moon rotation now since my first video I made about 3 years ago, and I got it completely wrong. And I put my hands up and say, you know what? When I made my first moon rotation video, I thought it was rotating because of this reason and that reason, and I got it completely wrong. You know what I mean? So I've gone back and I've looked at it. I've looked at Steve Tooth of the Lamb's work. I've looked at Chris's work, and I've just drawn my own conclusions from my own observations. And like I say, I've got these moons on my ceiling, and what I did, I put them moons in a position and I laid them out exactly how I observed the moon outside. Same declination angles and same azimuth. Yeah. Although the center of my room is slightly off, it's not facing south. What I did, I took the diopter, and if you go into the magnetic declination, you can change the magnetic declination on it. So I set it so the middle of the moons to either side of the middle of my room was my meridian line. So I actually calibrated the app. So basically made a meridian line in the center of my room as well. And what I found is you'll see it on the presentation. There's some weird stuff goes on. Like I say, they talk about the counterclockwise rotation, which I can explain, and it's quite simple to get your head around that. I was quite baffled when I found out about that, because like I say, the moon appears to rotate clockwise, but on the odd occasion you do get that slight counterclockwise rotation. But we'll look at that anyway. So yeah, so I don't know if there's any sound on this video. Can you hear it? No sound, right? I might as well turn the sound down then. No, I'm turning it down on the actual app. Yeah, so I was out shooting the moon the last month, and I noticed there was quite a few stars near the moon, especially that one you can see. I think you can just see it just there. Look. Now that star is called Hyodum 2, and I thought, I wonder if that star's going to pass the moon. So what I did, I got the camera out, and I basically set it up, and I just sat there and waited and waited and waited until that star got closer and closer to the moon. Then as it got closer, I zoomed right in with a P1000, right up to full zoom here. I'm at maximum zoom, 500 times zoom. And you'll see the star in a minute. It just appears in the top left-hand corner. There you go. So what I wanted to do, I don't know if you've seen my that there you got the moon, and there you got the star Hyodum 2. Yeah, it's just getting closer. Yeah. So, and as you can see again, look, it gets closer and closer. It's very similar to my the lunar occult of Aldebaran, the star occult before it went behind the moon. But with the moon being quite full, yeah, you couldn't really tell when the star popped out. So then what I did, I went onto Stellarium and I looked at the app and I found out when it's going to pop out the other side. Now, within half an hour, it would have been in the shadow part here, yeah. But it never appeared. And it took it took over an hour to appear. But as I was waiting for it to appear, the bloody clouds came in, didn't they? So I basically had to shoot the second part of the video through the clouds. So what I thought I'd do, I'd take the opportunity here just to zoom in on the moon and like show people the moon, very close. Yeah, it took about an hour for the star to come out, but like I say, it started getting cloudy, but I managed to catch it just. So I thought I'll just take the opportunity to shoot the moon and let everybody see it really, really close up. I locked the settings on the moon as well. That's why the moon appears quite bright on that side and quite dull on that side. You know what I mean? So yeah. So after about an hour, I checked on Stellarium when it was going to pop out the other side. Then an hour later, it just popped out, but I was literally fighting the clouds. I put the camera in manual movie mode, and there you can see the star just reappeared. You won't believe how many clouds I'm actually shooting through now. And the star, yeah. I had to put because of that manual movie mode on the camera, you can put the ISO really high, make the moon look really bright. And as you see, all the shadow, the basically disk of the moon, yeah, that star didn't appear until it had passed all that disk. You know what I mean? Even though we can only see half of that moon, yeah, that star didn't appear until it cleared the whole disk of the moon. Now, I know a lot of people have said in the past that they've seen stars through the moon. Now, you know, I've been observing the moon now for well over 3 years, and I've shot the lunar occult twice now. Well, I've never ever every star I've ever seen always goes behind the moon. I've never seen one go in front of the moon. And I know that Eric DeBay on his IFAs, it's still on his IFAs page because I went on there and I actually read the actual post basically where he reckons that Venus has been captured through the shadow part of the moon. Now, I've shot the moon on a number of occasions. Can you still see my screen? We'll do the presentation in this size screen because it's it'll just be easier for when I go through the slides because I don't want to go through every single slide. It might be a bit too much, like I say. So basically, yeah, what I've done with this presentation, I've called it Testing the Moon, a Global Eye Perspective. It was the Global Eye Convention, and I thought that'd be a nice little name to call it. You know what I mean? I normally call it from a flat Earth perspective because what I've done, I've made numerous observations over the past few years, and I've got friends who have made observations as well. So what I've done, I've basically drawn a conclusion from the back of them observations, as in, yeah, we don't live on a spinning globe. So what I've done, I've put together some of my own proofs, some observations from Jennifer, some observations I made from high altitude, from various YouTube videos, looking at the SL-10 amateur rocket, from the YouTube GoPro awards, to show that even at 396,000 feet, there's still no measurable curvature. So, like with every single presentation that I've ever put together, I will make a disclaimer and say, am I a scientist? No, I'm not. I'm not a scientist. Yeah, I've never done a PhD or anything like that. All the information in this presentation is my own beliefs. You know what I mean? I'm not saying these are the facts. I'm just saying that based on my observations, I've come to these conclusions. So that's what I just want to put out there. People say, yeah, you're making observations and you're doing scientific things, but I still don't look at myself as a scientist. I'm a warehouse manager from Sheffield. You know what I mean? So, like I say, I just make observations and I draw my conclusions from my observations. But you probably remember this from my previous presentation, because Brian Cox, I don't think he's really keen on these conferences or these conventions, what take place. And he did put this on his Twitter a couple of years back now. Perhaps they could put this quote below: "Everyone attending this conference is a shitbox." So that's Brian Cox's thoughts on conferences. So what I did, I found this little video on Brian Cox. You probably won't be able to hear this, but what he's saying is, there is absolutely no basis at all for thinking the world is flat. Nobody in human history, as far as he knows, believed the earth is flat. But if you look back, what you'll find is that every single ancient civilization in history knew the earth was flat. And I've just got a few examples there. You've got the Mayans, the Norse, the Hindus, the Incas. I remember you mentioned before the Native Americans, the Navajo, Arabic, Hebrew, even the Egyptians. You know what I mean? The Egyptian cosmology is quite clear to see that you've got the flat surface below, and you've got the firmament with the stars and the sun and moon fixed into the firmament, and that's been known for thousands and thousands of years. You know what I mean? So if you look at all ancient cosmology, yeah, it depicts a flat earth. Yeah. So when Brian Cox is saying, yeah, there's no basis for it, there's actually a lot of basis for it, because every single ancient civilization believed in a flat earth. There was only a few, like the Greeks, yeah, who believed it was a globe, but even then it was a stationary globe. And Ptolemy, who was probably one of the famous astronomers of all time, even in today, when they build planetariums, they build planetariums based on a geocentric model. And what they use, all the gears and the pulleys they used in these huge planetariums are based on Ptolemy's system of astronomy. They're actually based on his epicycles and his model. Yeah, so even like when you go to a planetarium, probably not the modern day planetariums because they're all digital now, but all the old planetariums, what they used to build, they're all based on geocentricity. So, and this is an interesting slide, because this is a guy called Cosmos Indicopleistes. Now, a lot of people probably think, who the hell is he? I'll just read this bit out for you. Yeah? Cosmas, basically, he flourished in the 6th century. Yeah, and he was a merchant traveller, and he was known for being a flat earther. And in his book, The Christian Topography, yeah, which contains some of the earliest maps, and that's actually his actual model. Yeah, what you find is, in a lot of ancient cosmology, they always add an object at the center, you know, whether it be a mountain, a tree. And what you'll find is, in the ancient cosmology a long time ago, they didn't know how to separate night from day. So what they did, they usually stuck a mountain or a giant tree in the center. So when the sun or the moon went behind it, yeah, that's why it disappeared. And that's why you see a lot of objects at the center of a lot of ancient cosmologies, because they didn't know how to separate night from day. Well, that's why Cosmos stuck this big mountain behind his. Well, obviously they knew a lot about the night sky, but they didn't know how to separate night from day by building a model. So what they did, they always stuck a huge object at the center. So when the sun or the moon went behind that object, it'll disappear. So when the sun disappears for like so many hours, in their model, it's usually gone behind like a giant mountain at the center of the cosmology. You know what I mean? But like I say, a lot of people say that flat Earth's a psyop and it was dropped on us back in early 2014 to see how we'd react. But when you trace these books back, I mean, the Vatican has all the old books based, like the books like Ptolemy's Almagest, the Christian topography. So these books can be traced back to the 6th century. You know what I mean? There's a lot of evidence to show that we've got books tracing back to as far as the 2nd century based on Ptolemy's Almagest or Cosmos's the Christian topography. So when people say, yeah, it's a flat Earth, it's been planted on in 2014, when you look into the history of it, you can trace this book back to the 6th century. And you know what I mean? Cosmos was talking about the shape of the Earth back then. He was actually debating his fellow monks back then. So is flat Earth a psyop? I'm going to say no, it's not a psyop, because you can trace it back thousands of years. Well, exactly. We've only been believed in it since Copernicus, which is like 500 years ago. Well, like I said, that's when we first saw the actual globe. You know what I mean? They've believed in a globe model for like 2,000 years. If you go back to Ptolemy or Hipparchus, yeah, exactly. I mean, that book Cosmos could have been planted there. We don't know. It's like 1984. They can change anything they want now, especially now things are digital. You know what I mean? It's so easy to change things. Yeah, where we've got the capabilities of recording in 8K now. You know what I mean? They just released 8K TVs. Yeah. So 2 seconds. Sorry, I just had to cough. So what I did, what I set out to do in this presentation, I set out to look for proof of the globe. Now, one of the biggest proofs that mainstream media will push on you is basically boats sailing away over the water. You know what I mean? Yeah, they tell us that the Earth's too big to see the Earth's curvature, but they'll tell us that boats will sail away at 4 miles. You know what I mean? And you can watch a boat. Yeah, they'll tell you. So what I did, I looked for some proof, and I went onto the internet, and I found Red Rhetoric proof of a boat sailing over the water. So what we'll do, we'll just watch this little video, and I'll just talk you through it. So basically, what he's done here is watch the boat sail away over a few hours, and is seen how it disappears hull first, proving that we live on a globe. But what I'll do afterwards, I'll show you a few slides, very, very basic slides on how the law of perspective really works. Yeah. And as you can see on his observations, it does appear that the boat's disappearing hull first. There it goes. Well, what it's doing, it's converging, basically. So what I did, I just took this basic perspective grid, and I just put a circle in the middle of it. Probably better if I go to full screen to show you this bit. So I wanted to just have a look at the true law of perspective. So all I did here, I took a perspective grid, yeah, and I put a circle in the middle. And all I did was just made that circle smaller. Oh, go back. Yeah, so what you'll see is the center of the object is always what you call the datum, or the center point. So everything converges to that center point. So what you'll notice is everything will converge. Every object that moves away from you will converge to that center point. So as you can see, it gets smaller in all directions. The problem is, when you're looking at perspective over land or over sea, the actual line becomes the datum line. Yeah. So everything converges to that datum line then. So when objects sail away from you, or like the sun or sets over the ocean, yeah, the ocean becomes that datum line. And what you find is it appears, obviously, that it looks like it's going over a curve. What you'll find on the ocean as well, because the ocean's undulating, or it's always constantly in motion, you got your tides, you got your waves, you got your currents, you know what I mean? And it builds up that little bit of a wall sometimes, so it does look like things are actually sailing over a curve. But in reality, it's just converging beyond your vanishing point. and you see it time and time again with the sun setting over the ocean. I'm sure Wide Awake showed a lot of videos on his channel with the setting sun, and as you can see, it's very simple. Just a little simple diagram showing that the line becomes the datum. Yeah, exactly. And there's quite a few videos out there. I don't know if you've seen the one on the American football pitch where the guy's got the camera and he basically walks from one end of the pitch to the other, and you lose his legs halfway across the pitch. You know what I mean? Due to the natural laws of perspective, because that ground becomes a datum line and everything disappears below that, even that short distance, however short a football field is. But that's quite an interesting, and this is my famous quote, what I've used in just about every single presentation. Today's scientists have substituted mathematics for experiments, and they wander off through equation after equation and eventually build a structure which has no relation to reality. So basically, everything going forward in science these days is theory. You got theory on top of theory. Everything's reverse engineered, you know what I mean? They presume that the stars are infinitely distant, yeah? So they reverse engineer everything back from that. If they want the sun and moon to be a certain distance, then they have to have these measurements, you know what I mean? So they start with the sun at 100 million miles away, yeah? And then everything's reverse engineered from that point. If you look at the distance in the so-called planets, yeah, you got Venus, which is like 2 million miles away. Mercury, which is like 2 million miles away, for an example. Then they put Venus at 4 million miles away, then the Earth at 6 million miles away, then Mars at 8 million miles away. You know what I mean? It's very, very basic numbers when you break it down, really. There is no real science. Exactly. You probably have to take 20 notes off to get the probably right settings. But I've added this actually to the presentation now. What this shows is a star trail pointing north for nearly 12 hours. And during that 12 hours, what you need to understand, according to the globe model, yeah, that the Earth would have moved along the ecliptic by half a degree. But as you can see from a 12-hour star trail, there's no motion other than the actual stars moving in a circular concentric motion. Yeah, there's no, from that latitude where that star trail was shot, obviously, the only way you would get star trails like that would be if you was at the exact center of the North Pole and you looked up at Polaris and you shot that time lapse. Shooting it from a lower latitude like that, you would obviously get that motion where the Earth's apparently traveling. Well, all declinations are based on the angle from Polaris, aren't we? So I'm at 53 degrees here. So if I get a compass or a compass app and well, it's at 53 degrees. You know what I mean? If I point the app up, it's at 53 degrees. If I travel down to Spain, yeah, it'll be 28 degrees. You know what I mean? The declination angle changes on Polaris based on your latitude. So that's how they get the latitude. It's based on Polaris being at 90 degrees north. Yeah, like I say, it's basically all I wanted to show was that the only motion that we see in the night sky is that concentric circle motion. There's no other motion. Yeah. Well, no, because obviously, yeah, they want to give you the opinion of the spinning, but they also they also tell us that we're also traveling around the sun at 67,000 miles an hour. What I'm trying to show there is, yeah, it's difficult to catch it, yeah, but basically, all I wanted to do basically was show that concentric circle motion. There's only one motion, and that's just the stars turning. Now, I'm sure you've heard of the Michelson-Morley experiment, but what people don't realise just how prolific Professor Michelson was. I'm going to read this out for you. Professor Michelson was one of the physicists foremost in determining the velocity of light. Whilst he has recently been described in the New York Times as America's greatest physicist, Yeah. So he was actually named in the New York Times back in the early 1900s as America's greatest physicist. This is not just some nobody. This is like one of the most well-known physicists ever. And it was he who, working in collaboration with Morley in 1887, made the most painstaking experiments by means of rays of light for the purpose of testing, verifying, or proving by physical science what really was the velocity of the Earth. To express this more clearly, astronomers have for a very long time stated that the Earth travels round the Sun with a speed of more than 8 miles a second, which is just under 67,000 miles an hour. Without in any way seeking to deny this statement, but really believing it to be thereabouts correct, Michelson and Morley undertook their experiments in order to put it to the practical test. Just in the same way that you might go to the greengrocers and buy a sack of potatoes, say 112 pound weight, you'd weigh them yourself to see if it was correct. That's what they did in this. So basically, let me just come out of full screen. More technically, the experiment was to test the velocity with which the Earth moved in its orbit around the Sun relative to the ether. So basically, what they did, they had a contraption which fired light in one direction, and what they did, they measured the speed of that light, the time it took to reach one part and come back to the same point, and then they faced it in the opposite direction and repeated the experiment. Now, if the Earth was traveling around the Sun at 67,000 miles an hour, what there would be a change in that light. Yeah, there would be a slight change in measurement. What they found is it was the exact same no matter what direction it faced. Yeah. So what he concluded in his experiment was that there's no motion, there's no detectable motion of the Earth moving through the ether, because remember back then they believed in the ether. Now, based on that conclusion, you've got two conclusions. Yeah, one is the Earth's stationary and motionless. Yeah, or you know what I mean, there is no ether. So what they did, instead of saying, yeah, right, there is no detectable motion, they basically abolished the ether on the back of that experiment. So from that point onwards, the ether was just a myth. Then it was just something like science fiction. And interestingly, that's when Einstein built his general theory of relativity based on the back of Michelson-Morley's experiment. What Einstein said when he did his presentation at Princeton University, I can't remember what year it was, but for an analogy, it says, imagine you're in a cart and you're in this cart and the cart's in motion. Now imagine that actually you're not in motion, the cart's standing still, and everything about you is in motion. So what Einstein was asking you to do then, forget about your God-given senses, forget about everything you can see in reality, yeah? Believe what I'm saying. So when you're in your car and you're driving down the road, he's basically telling you, saying, no, your car could be stationary and it could be everything else what's moving. Now, in reality, we know if we jump in a car and then wheels are turning, we know that car's moving and everything else is obviously stationary around us. You know what I mean? It's quite clear, but Einstein basically wanted us to give up our God-given senses and believe in scientism. So it's quite interesting how everything was built on the back of this real experiment, which proved that there's no detectable motion. But instead of drawing that conclusion, this simply says, yeah, well, there's no ether then. So that's how they got around it. But the only experiment ever, you got the Michelson-Morley, Michelson-Gale, Sagnac experiment, Aries-Fail. You've got numerous experiments which prove there was no motion, but they've all been forgotten now. You know what I mean? They don't get mentioned. They're not in the history books. They're not taught at school. So, but if you look back at it, what you'll find is there was actually an experiment to test the motion of the Earth, and it failed. Well, yeah, like I say, you know what I mean? We have at this moment in time. Now moving on to like the science of today. I mean, I know this is going back to the 1600s and the late 1500s, I think it was. Yeah, I think it was I think it was the late 1400s, early 1500s. So we got Kepler's law. So Kepler's first law, an orbiting body travels in an elliptical path around a central massive body, which is located at one of the ellipse's foci. A foci is a focal point, basically. So if you want to draw an ellipse, you basically have 2 points. And if you draw a piece of string, and then you pull that string taut, and then you draw a circle, what you'll draw an ellipse. So you keep the string nice and tight, and then you draw a circle. And what you'll do is you will draw an elliptical orbit, basically. This is what they tell us the Earth travels around the sun in an elliptical orbit. So what you get that elliptical orbit shape. So as you can see, you've got 2 focal points. So they tell us that the Earth orbits the sun, and the sun is in one of them focal points. So if the sun's in one focus point, what's occupying the second focal point? There is no second focal point, yeah? If you get a single point, you would get a concentric circle, yeah? But they're telling us that the circle's an ellipse. So here's an example of it, yeah? And there you can see the sun in one focus of the ellipse, and that second focal point is non-existent. Without that second focal point, the ellipse is destroyed. So it's quite clear to see, yeah, that what science will say to us is, yeah, we want you to believe in this. So they want you to believe in that the Earth travels around the sun in an elliptical orbit, and they tell us it's got 2 focus points. Clearly, it's only got 1 if the sun was in one of them focal points. When you ask a reputable scientist, where's the second focal point, or what occupies that, they says nothing occupies it. Yeah, it's a mathematical focal point, so it doesn't exist. You know what I mean? So in reality, yeah, how can the Earth travel around the sun in an elliptical orbit when there's only got one of the objects at one of the focal points, namely the sun? But interestingly, I've mentioned this before in previous observations, that all Kepler's law of planetary motion was built upon observations which were collated by Tycho Brahe. Now Tycho Brahe made his observations in the late 1400s. Was it late 1400s? Sorry, late 1500s. Yeah. The first telescope was invented in 1608. Yeah. So all Tycho Brahe's observations were made before the telescope was even invented. So it's not really a good building block for science. I know they had some quite interesting gadgets back then. They had the astrolabes. I don't know if you've heard of the Antikythera mechanism. The mechanism which is a bit like an astrolabe. It can predict eclipses and numerous other celestial phenomena. But like I said, don't get me wrong. I'm not saying these guys were stupid or they didn't know a lot. You know what I mean? They knew a hell of a lot. And the astrolabe was constructed in 2nd century BC, over 2,500 years ago. You know what I mean? If you look at the work on that, it's quite fine. It's like watchmaker standard work. You know what I mean? They was constructing them 2,500 years ago. So I'm not saying they're stupid, but I'm just saying is to build up the law of planetary motion without the use of a telescope, to me, is not a very good building block for science. Now, if you look at the kind of equipment we've got today, I've got the Nikon Coolpix P1000. I've got a B700. There's the P1000. You know what I mean? There's numerous cameras out there, and there's a lot of apps as well. Now, with the Curve Buster, what I did back in February, I was involved in an observation with Dr. John D. Do you know Dr. John D, Karen? Yeah, well, I've met him on a number of occasions. Now this is not just a nobody. Dr. John D is a well-respected PhD. You know what I mean? Is pretty clever guy. Interestingly, he's got his PhD in light. Yeah, which is a perfect. I can't remember the name of it, but his PhD's in light basically. So what we did back in February, I was asked to take part in the peer-to-peer laser observations between Brighton and Worthing. So myself, Roxanne, Dr. John, his team, and a few others. The Leo was there as well. Ruben came down on the Friday, and we made a few laser observations. Now, on the Friday night, it was it was foggy, and we couldn't see nothing. Yeah, so we basically give up on the Friday, and interestingly, on the Saturday, we got down there about tea time, and I wanted to just shoot Worthing from Brighton in the daytime so I could just have a look at it with the camera. And while I was shooting it, I saw a green light in the distance during the daytime, and I said to Roxanne, I said, just give Dr. John a call, because I can see a green light flashing on and off. So Roxanne called Dr. John, and they were just setting the laser up, and we could see the laser already, you know what I mean? So we knew that the conditions were right for making this observation. So we set it up. On that night, back in February, yeah, we did it. We did it on them specific days because it was a super low tide. I mean, as you can see there, the tide was really, really low, which let us get closer to sea level, if you know what I mean. So the cameras were set up 1 meter above sea level. This is the setup at Worthing Pier. This is Dr. John and his team. He also had a documentary team filming him on that night as well, which was quite interesting. There's a video out on YouTube, and maybe I can link that at a later time, and you can have a look at it, which was quite good. It was made by some students, and it's quite a good documentary. It's not a hit piece or a mockumentary. It's actually a good little piece of work. It's short and sweet, but it's really good. So as you can see, they're setting up at Worthing Pier. This is our setup at Brighton Pier. As you can see, we've got poles with lasers fitted in them, and they're all balanced. Obviously balanced on the top, you know what I mean, with the spirit level. So we're shooting across a level surface. This is a zoom of Worthing. Now, when I zoomed the night before, you couldn't see none of that. You couldn't even see them two red lights. What I noticed when I zoomed across was that there wasn't a lot of refraction as well. If you look at these lights here, if you get a lot of refraction, what you'll actually see two sets of them lights. You know what I mean? So straight away, we knew that the conditions were good for making this observation. We took various readings, and here you can see Leo and Roxanne Glenn. They're actually doing a humidity test there. So we tested the actual moisture in the air, and that was around about 70% moisture in the air, which is still quite high, really. You know what I mean? The lower the humidity, the better for the observations. We took various temperature readings, and as you can see there, the water temperature was 7 degrees. We also took various readings at different heights, from 1 meter, 2 meters to 3 meter, to see if there's a change in temperature in the temperature index as you got higher. And I don't know if you can see that closely, but if you look, the air temperature was 7 degrees as well. So the conditions were pretty perfect, really. You got the water temperature 7 degrees, and you got the air temperature 7 degrees. What you do, yeah, you've got that equilibrium, and you've got you know what I mean, you're going to get less refraction. If the water temperature is 7 degrees and the air temperature is 10 degrees, you're going to get refraction, or vice versa. If the water's 10 degrees and the air's cooler, you're going to get refraction, and you're not going to be able to get a good observation. But when the conditions are right, with the least refraction, you can see a hell of a lot further. And as you can see, the laser was set up at 1 meter. So both lasers from both observation points were at 1 meter high, which is 3.2 feet. And this is the shot from Worthing to Brighton. Now, if you look carefully in the distance, you can actually see the red laser from the opposite end at Brighton Pier. And same with my setup here. This is my setup at the Brighton Pier, and as you can see, the red laser, the green laser, but you can also see that green bright dot at the other on the other pier. That's actually Dr. John's laser at the opposite pier, which is 9.5 miles away. Now you're you probably think 9.5 miles, that's not a very long distance, is it? You know what I mean? It's going to look flat. But even on a globe, 24,901 miles in circumference, or 3,959 miles in radius, you're still going to get measurable curvature over that distance. You know what I mean? According to the globe Earth, yeah, there's still going to be measurable curvature. And there's another shot I took, and you can clearly see the green light. Yeah, obviously, you know what I mean. If you've because it was a super low tide, the water was so calm. Honestly, you never seen it like it. You can see a few waves there, but it was just so calm and settled on that low tide. It was scary. It was eerie. You know what I mean? There was no noise or anything. It was so quiet, and it wasn't till this is when the actual tide started coming back in. When we was obviously setting up the observation and the tide had gone out, it was just eerily quiet and calm. It wasn't until the tide started coming back in that you started seeing the waves. So as you can see again, you can see the light source from the opposite pier from 10 miles away, and this is our laser from Brighton, and that's the light source from Worthing. Here's a little video I shot now. I'm actually zoomed in on Dr. John's laser light source from 9.5 miles away. At this time, what he did, he put the laser down to 6 inches. He literally sat the laser on a rock, yeah, and it was 6 inches above sea level. And what you can see is you can still see that light source from 6 inches. Now, the likelihood of seeing that on a globe, based on the globe math, would be 1%. That is the actual odds of seeing that laser on a globe. And there you can see the I-360 in Brighton, just to prove that we're in Brighton. What we did during them observations, we was actually live, and we was talking to each other, and we was actually blocking the laser off. We're saying, like, block the laser, show the laser, block the laser, you know, to show that we're actually at each observation point. We showed the time, we showed GPS coordinates. So, you know what I mean? It was a proper observation, and it proved beyond a shadow of doubt that there was no measurable curvature over a large body of water. What we did as well, we used the Mick West Metabunk calculator. And what he did in his calculator, if you look at this second little box down here where it says with standard refraction, he actually made the calculation with the standard refraction in. So even with the standard refraction calculated into the distance, there should have still have been 28.85 feet of curvature between them 2 points. As I showed early on, though, there was no refraction. So really, the hidden distance should have been 35 feet. So at a distance of 9.5 miles, like I said, that laser was 1 meter, which is 3.28 feet. On a globe with a radius of 3,959 miles, which is 24,901 miles in circumference. Yep. So horizon should have been 2.2 miles. There should have been a 15.05 feet bulge. The drop should have been 60 feet, which should have been 35 feet of missing curvature. But there was no curvature. You know what I mean? We could see them lasers clear as anything from the time we started making the observation to the time we finished. Yeah, well, what's interestingly is now that Mick West has actually changed his Earth calculator now, you know. On the back of this observation, he's gone back in there and he's changed in his calculator, in his Earth curve calculator. Now you can't measure it over water. But the only way you can measure is actually over water. You know what I mean? The lands, you've got valleys, you've got hills, you've got mountains, you've got dips. The only way you can measure over a surface is by measuring over water, which we know the natural physics of water is to seek and find its level. What we've proved, yeah, that there's no measurable curvature over water. They tell us we live on a globe, and it's 70% water, so there should be quite a bit of curvature between them 2 points. So my question was, behind what curve? There was no curve. But like I say, according to his calculator now, you can't measure water using his calculator because he's changed it. You'd have to go back and see the Dr. John D's video where he actually shows where he's changed the Earth calculator. What mainstream will probably tell us though? I'm sure you've seen this one. What you're seeing here is a mirage. So basically, yeah, what mainstream will tell us is the only reason why we can see that laser light from them 2 points is because it's a mirage. Now, what we showed is when the conditions are right, you get the ocean and the air temperature right, and the conditions right, you don't get refraction, and you don't get no inferior or mirage. You know what I mean? You can see a lot further. Now, you shouldn't be able to see it a lot further because on a globe, you should still have that curvature dip. But you know what I mean? You're seeing further, yeah? So you should be seeing less really on a globe. You know what I mean? But what we proved beyond a doubt. So I'll just go full screen for this video. This is Jenna Fredo's zoom across Lake Ontario from Fort Niagara. Now this again uses the MIC West Metabunk calculator, and there should be about 500, and I think it's 516 feet of curvature between these 2 points. This is 30 miles over Lake Ontario from Fort Niagara, zooming in on the Toronto skyline. Same thing here with Jenna Fredo. The conditions are right, yeah. She's been to this point many times, and you can't even see the Toronto skyline. But what you can see, when the conditions are right, you can see further. And as you can see here, this little building, the Rogers Centre, that should be 500 feet below the horizon line. 500 feet. You know what I mean? That's a long, long way. But as you can see on a clear day, completely visible. That's a lot of horizon there, isn't there? You know what I mean? When you zoom back in on the P900, you get a wide angle lens on it. And just a quick one there, I'll just read this out. The Toronto skyline, so it was at 30.84 miles away, and Jenna was at Fort Niagara, New York. The Rogers Centre dome, it looks a little bit square there because the dome, they can open the roof on the actual dome. So it's 280 feet high. Lake Ontario is 243 feet high. So the base elevation of the Rogers Centre is 267 feet, making the total height of the Rogers Centre 306 feet above the lake. So Jenna's elevation was six foot, and that's being conservative because I'm sure that Jenna's not 6 foot tall. Yeah, so she was being conservative on that height anyway. You know what I mean? When she pumped it into the calculator. So the alleged curvature on that distance and at that height would have been 516.85 feet of drop. And you could clearly see the Rogers Centre. Yeah, and the temperature of Toronto and Fort Niagara and Lake Ontario were all within 5 degrees of each other. And the humidity, remember it was 70 degrees on them observations that we made in Brighton. It was only 43% there. So the humidity was perfect for shooting. And what Jenna did, she proved beyond a shadow of doubt, over 30 miles, there's no measurable curvature. But again, mainstream will tell you that you know what you're seeing is really the Toronto skyline is magically rising up from behind the curve. That's how you can see it. But this is quite an interesting picture. What Jenna did, based on the back of her observation, she went out and she shot this bottle. As you can see, the juice in the bottle, yeah. She shot this on a flat court, yeah, and she zoomed in from a distance. And even on that object, over a short distance, if you get the camera closer to the floor, you see that the light actually bends the images down. So you get that mirror image. And as you can see, if you look again, the actual light will actually bend the image down. So you do get light refraction, but what it does, it's just bending the image downwards. It's not curvature. This is what they're telling us is the curvature. But as you can see, the image is just being mirrored downwards. So really, in reality, the horizon is there. But because you're getting that mirror effect, because I don't know if you've ever drove along a road on a sunny day, when you're driving along, you get that haze off the road, and you sometimes get like a flash of light, don't you? You know, you get the mirror effect. It's the same effect. It just mirrors downwards. Yeah. So when the object is being mirrored downwards, it's not curvature. This is a flat court, and what it does, the image gets bent downwards. Clearly not curvature. But what is apparent is that the horizon is always at your eye level. So whether you're shooting across a court, whether you're shooting across Lake Pontchartrain, the horizon is at eye level. Remember we says about that image is being mirrored down. That's the mirror image there where it goes darker. It looks like it's curving over, but it's just a light bending the image down. So even at the beach, the horizon is at eye level. You go to Mount Everest, guess what? The horizon is still at your eye level. You go up to 120,000 feet, yeah, with a non-GoPro lens, and guess what? The horizon's at eye level, and it's still flat. So when does Earth start curving? That's the question. The only time you see curvature is when you're looking at something like Felix Baumgartner's space jump. Yeah, how a fisheye lens works basically. Yeah, when you get the horizon line in the center of the image, that's when you get a true representation of the horizon. So if you get the horizon line equidistance, you get the true straight line, and you'll get a horizon. When the camera is panned downwards, that's when you get the convex image, and when the camera is tilted upwards, you get a concave image. But as you can see, that image now, the horizon is not at your eye level, yeah? So the camera has been actually tilted down to give the appearance that the Earth's curving. So I'm sure you've seen this clip. So basically, this is Neil deGrasse Tyson referring to Felix Baumgartner's near space jump, and he's saying, you see Earth's curvature. He says, wow, he's in space. And Neil basically says, no, he's not. You don't see the curvature of the Earth when you're 2 millimeters above the beach ball. You just don't. That stuff is flat. So basically, what Neil's saying is, even at 128,000 feet on a globe, you still won't see no measurable curvature. So my question was, how high do you need to go before you need to start seeing measurable curvature? And what I did, I went on to the GoPro awards. Yes, they're using a GoPro lens, but like I've mentioned before, if you get the horizon line equidistant, you'll get a true representation of the horizon. So what I did, I paused the video. Now, the SL-10 amateur rocket went to 396,000 feet. That's a long way. That's 70 miles up. Yeah, it's a world record for an amateur rocket. Now, if you know anything about a GoPro lens, if you look at this horizon line, when you get the image equidistance in the center of the actual frame, you'll get the true representation of the horizon. Now, a GoPro lens also shoots a field of view of 180 degrees. So there's a hell of a lot of horizon there. Yeah, from that point to that point is 180 degrees. Remember, it's a GoPro lens, so you can actually see a field of view of 180 degrees. There's a huge amount of horizon at 70 miles up. And what you'll find is it's still flat. So my question is, when does Earth start curving? I mean, if you look at Philip Schofield, when Gary John and the team went on to the this morning, and he says, I've seen the curvature on Concorde. I was one of the lucky ones. I flew on Concorde at 50,000 feet, and I saw Earth's curvature. As we know, even Neil deGrasse Tyson, who, I mean, it's probably the only time I do believe him, has said, even at 128,000 feet, you're not going to see the Earth's curvature. So how the hell did Philip Schofield see the Earth's curvature at 50,000 feet on Concorde through them tiny little windows? He didn't. So another proof of Earth is images of Earth from space. And one of the first things I did when I found out about flat Earth was Google images of Earth. And it doesn't take long to realize that there is no images of Earth. What you'll find is they're all composite images. You know what I mean? NASA will even tell you that the only time they've claimed that they actually took a photograph of the Earth is when they're referring back to images of the Earth from the Apollo missions. But if anybody's seen a funny thing happened on the way to the moon, Bart Sabrell's documentary, where it shows you Buzz Aldrin and Neil Armstrong faking the Earth from low Earth. Well, they said low Earth orbit. I don't even think it was low Earth orbit. You know what I mean? Probably high altitude aeroplane to take truth. You know what I mean? When they put the little cutout of Earth on the window, then they pull the camera back and they black out all the windows, and it looks like Earth from a distance. And they're basically claiming that they're halfway to the moon. That's why the video was called "A Funny Thing Happened on the Way to the Moon," because they basically was faking the Earth. So there is no images of Earth, and even the ones they claim are images of Earth were faked anyway, which Bart Sibrel proved. And interestingly, on his follow-up video, Astronauts Gone Wild, where he approached all these Apollo astronauts and gets them to try and swear on the Bible, it's quite funny, you know what I mean? You've got Buzz Aldrin saying he's going to sue him if he shows that video, and you've got obviously Buzz punches him in the face as well, which is quite funny. But from when you look for images of Earth, what you'll find is you'll find cartoons. And a lot of the cartoons are made by this guy, Mr. Blue Marble, aka Rob Simon. I think I've got a bit of a write-up on him, actually. Let me just go back a slide. Yeah, so Rob Simon, lead data visualizer and information designer at NASA. So it says here, this is what he's wrote. It says, my role is to make imagery from Earth science data. I turn data into pictures. I look for new interesting events that NASA satellites have seen or that are hidden in the latest data to find anything interesting that shows off NASA's huge, unique capabilities. Basically, NASA sending some snippets, yeah, where they claim that they've been shot from a satellite, which they look like they could be from high altitude because they don't look like they're from the distances that they're giving. And he basically takes that information and wraps that information around a flat map and produces the blue marble. You know what I mean? He actually says he takes a flat map and he wraps it around a ball. Yeah. So, and you know his favorite quote is, "It is Photoshop because it has to be." You know what I mean? It's quite funny. I'll just play this. So we're told. So what are we told then? So we've been told that we live on a globe. Yep, and we're orbited by a single satellite, which is the moon. But based on the observations that I've just presented in the first part of this presentation, yeah, a lot of these observations don't fit that globe. Yeah. So what we need to do now is, you know, I've spent a lot of time looking into the moon, doing a lot of research on the moon. We need to look at the moon from a different perspective. So what I've done now, I've took a lot of my research over the last few years, and I've based it on a flat Earth perspective. So all the research going forward now is based on a flat Earth perspective. So that's what we're told. So testing the moon. So we know that there's no measurable curvature over large bodies of water. I've proved that with real observation. We know that there's no detectable motion. That was proven in the late 1800s, early 1900s by Michaels and Morley when they tried to detect the motion of the Earth. We know that there's no measurable curvature and the horizon always rises up to the eye level, even at 70 miles. Yeah. So there's a lot of observation and evidence out there that proves we don't live on a spinning ball. Yeah. So basically, what I've done now, I've drawn my conclusion that we don't live on a spinning globe. What shape the Earth is, I don't know. Yeah, the Flat Earth Society will tell you it's a pizza in outer space. We know it's not a pizza in outer space. A lot of my research from my previous observation disproved that model a long time ago, going back 2.5 years. So, but we do know that there's no measurable curvature over large bodies of water. The horizon is always flat. It rises to the eye level, and there's no detectable motion other than the rotating stars, which doesn't show you no motion of the Earth along the ecliptic. So my observations, what I've done here, I've used this in every presentation because what I've done, I've basically used an app on a phone, and I've placed it over a compass to see if the app is accurate. You know what I mean? What's point in using something like an app if it's not going to be accurate? So I line the compass up with north. I place the app over the top of it took a single snapshot, and as you can see, the azimuth on the compass app was 0, and the compass was pointing north. So it's pretty accurate, you know what I mean? The tools I use to make my observations, I mean, this camera has been brilliant. The Nikon Coolpix B700. Everybody bought the P900. I went out and bought the B700. I didn't like the size of the P900 at the time, and I thought, you know what, I've got a little camera. When I'm traveling, it's easy to carry around with you, and it's just as, in fact, it's probably a better camera in itself. You know what I mean? It's 20 megapixel. It's got raw images, which both the P900 didn't have. Don't get me wrong, the P900 is a bloody good camera, but I just like the P700, and it was recommended to me by the Nikon guy who was in the camera shop when I bought it. So I didn't know a lot about the cameras at the time. Like I say, I'd never even used a camera before that, so it was all new to me. So I went down, and luckily there was a Nikon guy promoting some stuff in there, and I said to him, I want the P900 in it, and he says, have you thought about this camera? It's cheaper and it's better. So I ended up buying the B700. But since then, I've took the dive, and I've purchased the P1000, and it is a hell of a camera. Yeah, it's not as high resolution as the B700, but that 3000 millimeter 125 times zoom with a digital 500 times zoom is absolutely awesome, and you can get some really clear shots. And like I mentioned before, I used a camera app, and the app I used is Dioptra. I'm sure you're quite familiar with this, Karen. Yep. So I'll just read out the description what they give on the app site. It says Dioptra, a camera position and angle measurement tool for navigation, surveying, positioning, and measurement. So you know what I mean. They say it's for surveying, positioning, and measurement. So that's what we're using it for. And it says Dioptra provides the following information like a theodolite optical instrument. Your indicator, basically a compass, pitch indicator, so your tilt in degrees, so basically how many degrees above the horizon or below the horizon. Roll indicator when you're tilting it left and right, along with GPS position, so it's using GPS. We all know that's ground-based and not satellite-based, so let's just clear that up, yeah? People say, yeah, you'll be using globe Earth math. I'm using the app for the position of the moon and the angle of the moon. That is all. And basically, it's an azimuth and bearing to photo subject. So you can take an image of the moon with a timestamp on it, then you can take a Dioptra reading afterwards, and you can use your image for the timestamp and the date, and you can use your Dioptra reading for the azimuth and the declination angle, which is a good combination. And like I say, you don't need to be a scientist to make observations. You need a camera and an app tool. So what I've done here, I've just took a simple shot of the moon. And there you can see, it's quite a recent one. If I come out of the full window, you'll be able to see it a bit better there. So I took that on the 20th of August, 2019. So it's quite a recent shot. Like I say, I've been updating all my observations now. So although I made a lot of observations with the B700, I have to carry that on because I made my previous observations at the same resolution, using the same focal length. I have to carry that on. But when I'm starting repeating observations, I'm repeating it now with the P1000 and still getting the same results. So all I did here, I took a simple single frame shot of the moon when it was at my zenith. What I did to see if the phases were matching up, I went on to NASA's Lunar Reconnaissance Orbiter, and what you'll see there is we've got quite a lot of information on here. You can see I've got the correct phase. If you look at the phase, it's pretty much spot on. But also, what you'll notice, according to the globe Earth, that the moon is at its furthest point at apogee. So you've got your closest point, which is apparently 28 Earths away at perigee, and the moon apparently moves between 2 points, the closest point and the furthest point. The closest point is perigee, which is 28 Earths away, and the furthest point is apogee, which is apparently 32 Earths away. And a lot more information on here. Obviously, you've got the distances down here. It's got it in kilometers. I don't know the distance in kilometers, but we know they claim it's 240,000 miles away. You know what I mean? We know it's not that far away. Just simply by the moon lighting up the clouds locally. Yeah, you'd never be able to see an object that far away. It's ridiculous. So there's quite a lot of information on there. And obviously you can see there it's got the phase at 81.6%. So there's quite a lot of information we can take for that. Even though we're looking at the globe Earth model, we can still take a lot of information from the moon, from the information from the moon. So for example, if you wanted to measure the eccentricity of the moon, basically, they're saying there's a closest point and a furthest point. That's called the anomalistic cycle. What you can do, you can measure the moon when it's at the furthest point according to the moon phase model, and then you can measure it at the closest point and see if there is a measurable difference. If there is, then you can say, yeah, there is an anomalistic cycle. So, you know what I mean? You can basically tick that box and move on to the next set of cycles. But we'll look into the cycles a bit closer later on, because I've been through quite a few of the moon cycles, and there's quite a lot to get your head around, and they're quite mind-boggling. So again, what I did, I also took a diopter reading. A lot of my observations have been made when the moon's at my zenith or the meridian passing, which is always 180 degrees in the northern hemisphere. As you can see there, my readings, I face the app at the moon, and according to diopter app, the moon was 178 degrees azimuth, the direction I was facing, and it was a declination angle of 38.5 degrees, so the moon was 38 degrees above the horizon. What I did then, I went on to MoonCalc to see what their information was saying, and as you can, if you look there, the moon azimuth, the moon was 179.8 degrees, and the moon altitude was 38.2 degrees. So pretty close, 1 degree out in the azimuth, and 0.3 degrees out in the declination angle. So what you can probably conclude is that the observations I'm making are pretty accurate. Yeah. So the moon is where mainstream says the moon's facing. We can conclude based on observation that it's facing in that direction. It'd be a bit silly if you took a snapshot of the moon and MoonCalc and time and date said it was 180 degrees south, and the app said it was something like 270 degrees west. You know what I mean? Then there'd be questions asked. So this is a little video now. What I did here, I took that image, that single frame image, and I basically show you how I measured the image. So I'm using professional software. This software is really, really expensive. It's not free. You know what I mean? This is what surveyors use, map makers and all sorts to measure distances. You can plug formulas into it and all sorts. What I'm doing here, this is not an accurate measurement. I'm just giving you a quick demonstration on how to measure the radius of the moon. Yeah. So I'll basically take 2 points. Click it there. I get a measurement of 2,345 pixels. Now I want to merge them measurements into the image. Yeah. So at that resolution, I have to merge them in, and it obviously looks quite big there. But when you zoom back, there you can see the actual image. That's just to give you an example of how I measured that image. You can measure the circumference, you can measure the radius, you can measure the length, you can measure the width. You can just about measure anything you want, you know what I mean? So you've got quite a lot of scope to make quite a few observations. And like I say, when you're looking at things like the anomalistic cycle, which is where the moon appears bigger in the sky and smaller in the sky, what you can do, you can actually measure it and see if there is a measurable difference. And there you can see the finished product. So there you go, the same moon image. And all I've done now, I've measured 2 points, basically the radius from the top to the bottom, and it worked out at 2,345 pixels. Is that pretty? Yep. And so So now we're moving on to my observations. This is a shot I took. I can't remember I took it. I took this shot a few months back. Basically a full moon. I saw the full moon rising. I thought, wow, that moon looks absolutely massive. Have you ever looked out the window and seen a red moon and it looks huge? It's massive, isn't it? Yeah, but obviously, you know what I mean? We weren't taking much notice back then. Now we're taking... Now, yeah, well, like I say, when it's in open space, it will look tiny. But as you can see, I've actually... Well, let me just... I'm going to just... I've just got this book out here. You can't see it. What I'll do, Can I... No, what I'll do, I'm not going to come out of the presentation. I'll keep it in the presentation. But basically, what I did, I see the moon illusion, and I thought, oh, I wonder if there's any books on the moon illusion. So I went out, and I found 3 books. Yeah, what I did, I found 3 books on the moon illusion. I've got all 3 books. And you know what? These books are all got like 300 or 400 pages each. And there's not one conclusion or one definite answer to why the moon appears big on the horizon. Yeah, it still hasn't been solved. Yeah, they've been looking at the moon illusion for thousands and thousands of years. Aristotle tried solving it. Ptolemy tried solving it. Hipparchus tried to solve it. Even Da Vinci tried to crack this one. Yeah, and failed. Nobody can crack the moon illusion. It's just something that's never been proven. They say you can't catch the moon illusion on camera. I disagree, because as you can see on this image, if you look at the houses and the trees down here, they're tiny. Look how big that moon is compared to these houses and these trees. So they say you can't catch the moon illusion on camera. You can, but there is something very, very strange going on with the moon. Yeah, on the verge of being supernatural. One of the reasons why they probably never solved the moon illusion as well, because a lot of it's been based on the heliocentric model. When they're trying to solve a problem like this, a supernatural phenomena, with a mathematical model, it's never going to happen. You know what I mean? You can. That's why it's never been solved. That's my answers anyway. So, although that moon looked massive, what I wanted to do, using that bare soft measuring tool, I measured it. So when that moon was on the horizon and looked absolutely huge, I measured it. And what I did as well, I also took all the metadata from the image. Now, if you look at the actual focal length of the image down here, you'll see the image at 258.0 millimeter focal length. That's the equivalent of 1440 millimeters. Basically, that's the optical zoom on my B700 camera. It can't zoom anymore. Yeah, unless you go into the digital zoom. But what I did with my observations, I always made the observations at full optical zoom. So there was no, you know what I mean? If you start messing about with digital zooms, you're going to get variations and you're going to get discrepancies. So all my observations were made at the optical zoom, which is 1440 millimeter, which is the equivalent to the focal length of 258.0 millimeter. I know that's a bit confusing, but basically it's 60 times zoom optical. Yep, so as you see the focal length there. I also took a moon count reading. There you can see the moon is on the horizon. Quite low, look, it's only 1.93 degrees above the horizon. And it's an azimuth, so the moon's facing 170 degrees east. Yeah, just obviously it's just risen. It's because of the time of the year. If you look, it's like just after April. Yeah, the full moon always rises slightly below. Yeah, in the southern hemisphere. I've showed this on the sun and moon a few times. When the sun is high on the Tropic of Cancer, the full moon is always low on the Tropic of Capricorn, and vice versa. And what you'll notice is, as that sun gets declination throughout the year, that full moon gets declination, and they basically switch. So when it comes to winter time and you've got the sun low on the Tropic of Capricorn, then you'll have the moon, the full moon, super high on the Tropic of Cancer. Yeah, so they switch, and as you can see there, it's just before the solstice, and the moon is just rising, still in the southern hemisphere, in what they call the winter hemisphere. Could be a reason why moonlight's cool as well, because when they do these moonlight tests, they always do them on a full moon, and the full moon is always in the opposite hemisphere to the sun, so it's always in the winter hemisphere, which is quite an interesting point as well. But as you can see there, the moon is rising. What I did then, I also waited till the moon reached my zenith. So to the naked eye, that moon looked absolutely huge, and it really caught my attention on the horizon. But when the moon was at zenith in open space, it looked tiny. It looked literally it looked a quarter of the size of the moon on the horizon. And as you can see there, I measured that moon using the measuring tool again. Also pumped that data through the program to get the metadata. And as you can see, you've got the model, Nikon Coolpix B700. And again, you've got the most important point, the focal length, which is 258.0 millimeter, which is equivalent to 1440 millimeter, which is 60 times zoom on the B700 camera. So I took the image from the same point using the same focal length. Yeah, so I can keep my observations consistent. What I even started doing recently, not on this observation, but I've actually got a laser thermometer now, or an infrared thermometer. I actually started taking regular lens temperature readings as well, to make sure that I wasn't getting inconsistencies from the changing temperature on the lens. So, you know what I mean? I'm always improving my observations and finding new ways to, you know what I mean, make my observations. So that's something new what I will be doing going forwards. When I make these observations going forward, I will be taking regular lens readings as well with the infrared thermometer to make sure that there's not a huge difference in change of temperatures. So there you can see again that moon shot. It's at 180 degrees at my zenith, or at the meridian crossing. So the moon has gone from rise to my zenith. Interestingly, when you put the moon side by side, what you'll see is that huge, gigantic moon on the horizon actually measures smaller than that tiny little moon at my zenith. Look at the width. You're always going to get a little bit of compression. Exactly. What I'll show you in a minute, I'll show you a couple of illusions. So let's just confirm this first. So the width of the moon was 2011 pixels. When it was on the horizon. The width of the moon when it was at my zenith was 2048. So there's a significant difference in the actual width of the moon. Mainstream will claim that the only difference in size should be in the actual height, which we see that anyway there, but there also is a measurable difference in the width of the moon. Now, I've made this observation 6 or 7 times and documented it 6 or 7 times. If you look for my moonrise to zenith, my moonrise to zenith beyond, my moon illusion posts on my lunar cosmology page, you'll see you get the same results every time. When the moon is on the horizon, it measures smaller, and when it reaches my zenith point, the highest point between rising and setting, it always measures bigger every single time. Even my latest one, where I took regular lens temperature readings, and I used the exact same settings. I didn't only use the same focal length, I used the same aperture, I used the same ISO settings, and I used the same f8 setting, right? Everything was set identical, and I still got the same results with the Nikon Coolpix P1000. So this is observable, measurable, and repeatable. And I've repeated it 6 or 7 times now, always with the same results. So what's happening then? So the moon appears huge on the horizon, but it measures smaller. Now, this is taken from the nasa.gov website. I'll read it out for you. It says, these views of the moon were taken on June 9, 2017. The orange-coloured rising moon on the lower left had just cleared low cloud on the horizon around 8:30 p.m. The high moon image, top left and duplicated lower right, was captured around 950. The full frames of the images are presented here, and the green line illustrates that the horizontal diameters of the left pair of images are the same. So what they're saying is, there's no measurable difference between the actual width of the moon, but I've showed you that there is measurable difference, yeah? But the main point of this slide is to show you, yeah, yes, they do claim that there's a change in size, yeah, when it's on the horizon due to atmospheric compression. Well, we'll get to that, but in a nutshell, if the moon is closer than predicted by mainstream, yeah, it would appear smaller on the horizon, although the illusion makes it look bigger. And as it rises to its closest point, or the observer's closest point, it's going to be closer to the observer, isn't it? So you would see a measurable difference, and that's what we're seeing based on my observations. Yeah. If the moon was 238,000 miles away, yeah, you would not see a change in angular size between rising and setting. And what I'll prove in my observations using moon count data is that according to the globe model, on some of these observations where the moon measures bigger, it's actually 300 or 400 miles actually further away from the observer based on the heliocentric model. So how's it getting bigger? The only reason why it could get bigger if it was smaller and closer than depicted by mainstream. But it says here, step outside in the evening or sunset and look around. You'll see a giant moon rising. Yeah, it looks like Earth's moon, round and cratered. The man in the moon is in his usual place, but something's wrong. The full moon is strangely inflated. It's huge. You've just experienced a moon illusion. Sky watchers have known for thousands of years moons hanging low in the sky look unnaturally big. Cameras don't see it. I've proven that they do. Yeah, but our eyes do. It's a real illusion. There is an illusion there, but it can be captured on camera. Yeah. Interestingly, if you look at some of the other NASA information on the moon illusion, how they tell you to measure the moon, if you get your index finger when the moon's on the horizon and stick it out at full length and put it in front of the moon and use your finger to measure the moon. It's 2019 and they're asking to measure the moon with my finger. Yeah. You know what I mean? I'm using very, very expensive measuring equipment to measure the moon. I'm getting real accurate results. And to prove how accurate they were, recently I've just measured a load of globe images for Paul on the plane for his latest presentation. And what I found is my measuring of the globes was very consistent. Yeah, he sent me 6 images and I got the same measurement on all 6 images, set at different times according to the information data that he got off the satellite bollocks website. So what I did, I showed that my observations are accurate. I got the exact same pixel count on all 4 images. You know what I mean? And we're talking very high resolution images as well. We're not talking like 640 by 480. These images, what I got here, are 16 million pixels or 20 million pixel images. You know what I mean? They're very high resolution. So, as you can see there's the full image, what I took of the moon on the 19th of April this year. And you can clearly see the moon illusion captured on camera. But as I've proven with the actual measurements, it measures smaller. So what we perceive is basically, this is what we perceive. See this one here, the moon on the horizon looks huge, and as it approaches zenith or the highest point in the sky, it appears to get smaller. But what actually we see is that the moon actually gets bigger, even though you can't really see it with the naked eye as such, although on that moon illusion image, yeah, on the actual image itself, you can see that there's a measurable difference. It looks big with the naked eye, but side by side, you can clearly see that moon on the horizon is a lot smaller than the moon at zenith. So that's what we perceive, and what actually we see is the moon gets bigger. So this is the Ponzo illusion. Now you see the two horizontal lines. Well, the one down here actually looks smaller than the line above, doesn't it? But actually they're the same size. Yeah, they're the exact same size lines. So there could be an illusion with the moon. Remember, when the moon's on the horizon, it's set against the background. When it's at your zenith, it's in open space. So there's nothing to really compare the moon with, is there? So when the moon's on the horizon, you know, you've got trees and you've got houses, you can actually compare the moon with something. And I think there is an illusion there. But what I've proved with real observation and measurement is that there's no, that there's actually smaller. So if we look at the data from them two images, from when the moon rises at 8:32 to when it was at my meridian or at my zenith at 1:39, just have obviously in the next day. So look at the moon distance according to mainstream. So the moon was 369,834 kilometers away from the observer. Now we saw that the moon appeared obviously measured bigger as it got to my zenith with real observation. But look, according to because the moon was heading towards apogee according to mainstream, when the moon was at my zenith, it was actually 370,670 kilometers away from the observer. So it's actually further away, yeah, but it's measuring bigger. Although it looks smaller, in reality, that moon is getting bigger as it approaches. But according to the mainstream, that moon should be getting smaller in their model. Yeah. Look, 369 on rise and 370. So because it's heading towards apogee and they give us these ridiculous distances, the moon is 700 miles further away from my first observation to my second observation at zenith. What that proves is that the moon's not 238,000 miles away. It's close, it's local, and there is a measurable, and you can measure it. And what I've done here, this is just to show you again that you can measure the moon from moonrise to zenith. So when the moon was low on the horizon, if you just look at the width and the height, you've got width 2108 in pixels and a height in 2056. As you'll see is the width 2110. It's getting bigger. So as the moon is approaching my zenith, you get bigger. There you go again. Look, it's 2127. Did you notice that then? Remember that there's been quite a lot of talk about that counterclockwise rotation. Well, I actually caught that counterclockwise rotation, and we'll talk about that in a minute. Yeah, but normally the moon rotates the other direction. So again, look, now it's like 8 o'clock and the moon is getting bigger again. The pixel count is getting bigger. So the moon is actually, as it approaches my zenith, it's actually measuring bigger. It's now 2150, 2148, 2157, 2156. And as the moon hits my zenith, it's 2193 for the width of the moon, and the height's 2189. What you'll see is my first observation 2108 and 2056 compared to the last one, which is 2193 with a height of 2189. So that's a significant change in size. Yeah, real observation, all captured at the same focal length, showing that the moon does actually increase in size or angular resolution between rising and the closest point at zenith. Yeah, I've had to come out of the window a couple of times, but what is apparent, yeah, is between them observations there is an apparent rotation of the moon, and what you'll notice is between 10 o'clock and 1 o'clock there's a huge change in rotation. Now I've had this discussion with Steve from Tooth of the Lamb. I've had this discussion with Chris, yeah, Mr. Thrive, and we're not going to see eye to eye on this. Yeah, you know what I mean? They've got their observations and their conclusions for this, and I've got mine. But what I'm going to do now, I'm going to give you my observations and my conclusion of why the moon rotates. So as you can see, you've got that slight rotation backwards there. The only time you see that counterclockwise rotation is when the moon rises north of east or sets north of west. You only see that counterclockwise rotation when the moon rises north, yeah? So to look at the moon rising north, yeah, you need to be facing north. Now, as you know, in Australia or below the equator, to observe the moon, you need to be looking north. And guess what? Which direction does the moon rotate in Australia when it rotates? It rotates counterclockwise. The simple answer to that question is the moon appears to rotate counterclockwise is because you're looking in a northern direction. When it rotates clockwise, it's because you're looking in a southern direction. But we'll get to that in a minute. So, the moon rotation. I'm going to give you my conclusion on why the moon rotates now. And I'm hoping Chris and Steve are watching this presentation because, like I said, I've spent 3 years looking at the moon rotation. Now, I will put my hands up and I'll say, do you know what? 3 years ago, I got it completely wrong. Yeah. But based on my observation and what I've actually learned over the last year, I think I've got a definite answer for this. And the tools you need to capture the moon rotation is basically a DIY moon rotation kit. Basically, 4 A4 images of the moon, blue tack, and a pair of scissors. What I did, I cut out the moons and I laid them across my ceiling. Basically use 4 moons because I only needed 2 really, but what I wanted to do, I wanted to see to give it a visualization, and by having 4 moons you can actually see the visualization of the moon rotation. Yeah, so I basically fixed them 4 moons on my ceiling, all at the same orientation. So if you look at the moons, they're all facing in the same orientation. What I did as well, I actually calibrated the Ultra app, so the center of my ceiling was my meridian passing. This is so I can actually measure the actual rotation of the moon. Yeah, obviously it gives me an east and it gives me a west, and it gives me an azimuth, so I can have a direction the moon's facing, and it gives me a declination angle. As you can see there, the moon, which from my latitude, when the moon's high on the Tropic of Cancer, the moon's around about 53, 54 degrees. So I've got it pretty spot on, yeah, for the moon being at its highest point on the Tropic of Cancer, which, if you go back to my observations here, these observations, obviously, if you look at the actual date, remember, the sun is low on the Tropic of Capricorn and the moon is always high on the Tropic of Cancer during the full moon. So the moon was really high on the Tropic of Cancer as well. So what I did then, I set my camera up in position so I could actually shoot the moon closer. So I took doctor readings of all the 4 moons and actually took close-up shots of all the 4 moons. Now, so this is my first shot facing southeast with the doctor app. And as you can see, got your azimuth there and you've got your declination angle. So as I move the app now from east to west, even though the moon's running on my ceiling, what you will see is it's not actually the moon. If you just concentrate on the moons, what you'll see is it's not actually the moons that rotate. It's the actual angle of the camera. You see that? Yeah. Now, Chris says, no, it's not. It's the moon that's rotating. I'm showing you here with real observation, yeah, that it's the camera that rotates. Now, if we go to the close-ups of the moon, yeah, so that's the first moon on the left. Now, and as I pan the camera to the right, guess what? The moon appears to rotate. Not only does it rotate, Karen, but if you look at the actual angular size of the moon, it appears to grow. Remember I said the moon is a lot closer than depicted by the mainstream science. You actually see the change in angular size of the moon as well. So it actually captures the change in angular size as well. Well, it's not an illusion. It's just that the camera is rotating backwards and it gives the appearance that the moon is rotating clockwise. Now, if you take my observation back on the 20th of January, which was the night of the lunar eclipse, yeah, what you'll see is the declination angle on the moon on that shot was at 51.70 degrees. On my ceiling, my declination angle was 51.6 degrees. Yeah. When you look at the Wesley one, when the moon was at 55 degrees on the real world shot, and on my shot on the ceiling, it was at 53.5 degrees. Is it a coincidence, or is it uncanny that I get the exact same amount of rotation? So what I did there, basically, I proved that the moon doesn't rotate. Yeah, I know Chris and Steve will say, yeah, but Phil. Well, if you look at this, right, this aeroplane is passing over from north to south. And what you'll see is, as it passes over, it appears to rotate 180 degrees. I know it looks like it's going to crash, but that's just due to perspective. But when you're looking at the moon, yeah, like you've just said then, the flipping moon, when you're looking at it from the north and you're facing in a southern direction, you see this moon. If you're looking at the moon from the south and you're facing north, you see the moon from that direction, because you're looking at the moon from the opposite direction. So this again proves that the moon doesn't rotate. It's just due to our perspective why the moon rotates. Nothing to do with any fancy moon rotation. What I've done there, I've showed with real observation, yeah, why the moon rotates from a flat Earth perspective. Nothing to do with equatorial mounts proving flat Earth, proving the globe Earth, because equatorial mounts, like I've shown you on star trails, just lock onto the stars, and there's only that one concentric motion, which completely debunks the heliocentric model. So they call that crazy, by the way. Yeah. So you're looking at the moon from a flat surface from two different observational points. They call that crazy, but they call that normal. The only way you're going to get me stuck to the bottom of that ball is by using a magic force called gravity. Yeah. But they call that normal, and they don't question that. They question that, but they don't question that. That's science for you. Everything's tipped on its head upside down. I hope that was come across pretty clear. Yeah, and like I say, if Chris wants to come back and give any feedback on that, I'll be gladly accept any feedback on it. But real observation, based on real observations in the real world and based on observations, exactly. You've hit the nail on the head. It's that simple. That's why when you go to places like Fuerteventura, and when the moon's high on the Tropic of Cancer, then the moon appears to do that 180 degrees flip like it does in Mexico. Because when you go to Mexico and the moon's high on the Tropic of Capricorn, yeah, the moon rises above your head and you have to turn 180 degrees to watch it set. And it's that turning what gives the appearance that the moon's rotating. That's why the moon rotates 180 degrees on the tropics, but it doesn't rotate 180 degrees in the northern or southern latitudes, you know what I mean? Like in the UK or southern Argentina. Hello, Mr. Blue Sky. Hello, Mr. Blue Sky. Yeah. There's been a lot of questions. Can you see blue sky? Can you see the blue sky through the daytime moon? Yes, you can. But what I'm going to show you here is there is a reason why you can see the blue sky through the moon. I took this image straight off the IFA's webpage. Yeah. And what it was Eric Debay telling us that Venus had been shot through the daytime moon. Now, I showed you that video when we started the presentation, didn't I? I filmed 2 lunar occults. All right, they were both at night time, but what you'll find is that stars always pass behind the moon. You'll never see the moon through the shadow part of the. You'll never see a star. No, Venus always gets occulted by the moon and always transits the sun. Yeah, in November, there's a phenomenon coming up, and what we'll do, we'll get Mercury transit the sun. It will transit in front of the sun, but it always gets occulted by the moon. You go back and look at any occults of any wandering stars, Jupiter, Saturn, Venus, and they all go behind the moon, regardless of the phase. There's thousands of videos on YouTube from years ago, which has got nothing to do with flat Earth, just basic astronomy videos. Yeah, only Mercury and Venus will transit the sun, which tells you that the sun is slightly further than the moon. But as you can see there, you can see Eric claiming that you can see stars through the moon. Now, when I went to Fuerteventura, I was looking at the mountains in the distance, and guess what? They look see-through. They look translucent. Now, I'm not saying the moon's a solid object or it's made of rock, but what I'm trying to say is when you look at an object from a distance through light, the light can do a lot of things. Yeah? And what it does, because we're looking at the things like these mountains through the daytime while the sun's out, yeah, what happens is we're looking at it and the shortwave light, yeah, it scatters very easy. And when it scatters, it turns blue. You know what I mean? And also what it does, it causes this kind of illusion where it looks like. Exactly. What it does, it proves 2 things to me. Again, it proves that the moon's not far away. I'm not saying it's a solid object, but with it being like that object in the sky, it's close. Yeah. I don't know how far the moon is, but when you look at the moon light up clouds locally, yeah, it would never happen from 238,000 miles away. Yeah, but yeah. So what I've done here, I've took a shot of the moon, and I've overexposed a crescent moon. And what I've done, even during like when it's still light, yeah, the whole disk of the moon is present, regardless if it's day, night, whatever time of day, whatever day or night it is, whether it's a crescent, whether it's a half moon, the disk is always present. It's just not visible. Sometimes because that white light scatters, it doesn't give us that opportunity to visualize that the ultraviolet light is invisible. Yeah, light at the ultraviolet end of the scale. See this shot here? This is a daytime shot of the moon. And as you can see, it looks like you can see the blue sky through the moon. If I put a filter on that actual moon, I can change it into a nighttime moon. Daytime shot, the original shot, and I just change it into a nighttime moon by changing the filter on it. Now you can see what. Yeah, now you know why you can't see blue sky through the moon. You can, but in reality you can't. The colour of the light spectrum can be seen through a prism or a rainbow. The colours in order are red, orange, yellow, green, blue, indigo, and violet. Red has the longest wave. So if you look at red in the infrared end of the scale, it has the longest wave, and violet having the shortest wave. This means the shortest wave of light will scatter and not be able to penetrate the denser layers of atmosphere, and the longest wave of light will be able to pass through the medium, thus making the moon appear a reddish orange when rising and setting. And there is also invisible light at either end of the scale, namely infrared and ultraviolet. So there is light that we can't see. Yeah, we have ultraviolet light, which we can't see, and infrared light, which we can't see. And they what you'll see is when the moon rises and it's red, because we're looking at the moon through a denser layer of atmosphere, that shortwave white light can't penetrate through that denser layer of atmosphere. Only the long wave infrared light can penetrate through that denser atmosphere. That's why the moon will appear reddish orange on the horizon, and that's why it appears whiter in the sky when you're looking at it through thinner layers of atmosphere, and the white light scatters. I think I'll give an analogy in a minute. Yeah. For an analogy, imagine the light spectrum is like the sound spectrum, 7 notes on a scale. When the sound vibrates your eardrums, yeah, you'll hear a high-pitched sound. Yep. So when your ear bones vibrate quicker, it creates a sound. There's no sound coming out of my mouth. Yeah. All you're hearing really is vibrations in your ear. Yeah. There's no sound coming out of my mouth at all. You're hearing vibrations in your ears. Yeah. So when you hear that high pitched sound, then bones in your ears are vibrating faster, which creates the sound, and your brain obviously creates a sound in your head, kind of thing. So when it vibrates your eardrum slower, you're hearing a low pitch sound like oh, yeah. Your bones in your ears vibrate slower. So I don't emit any sound from my mouth, only that your ears, yeah, pick up the waves and vibrate them, and it creates a sound in your ears. So that's a little bit like the light spectrum. Yeah, there's sounds we can't hear. Bats make an high frequency sound we don't hear. Yeah, and there's light at the end of the ultraviolet scale, what we don't see. And also, crocodiles make a very, very low rumble noise, which can't be detected by the ears. And there's infrared light, which can't be detected as well. So imagine the sound spectrum like the light spectrum, if that makes any sense. That might be a little bit of a head wrecking thing, but anyway. So moving on. So what I've done when I'm testing the moon, I've looked at the various moon cycles. So one of the main ones I've looked at is the anomalistic cycle. So when they say the moon's closest point at perigee, it should appear bigger, and when it's its furthest point at apogee, it should appear smaller. So what I did on the 23rd of the 8th, 2018, I measured the moon. I always measure the moon at the same focal length and at the same position. So always when it's at my zenith, and there you can see it's at zenith. I also looked on NASA's moon model to see if it was at its furthest point at apogee. And then I used that Bearsoft tool to measure the actual radius of the moon. So I measured it from the point to that point there. And it was 1,822 pixels. Repeated the experiment when the moon was at perigee. Again, at my zenith. There's the confirmation with MoonCalc. And there's a confirmation to see, according to the NASA model, it's at perigee, its closest point. And as you can see, it measured 2128. You put them images side by side, and there is a measurable difference. So there is actually a point of apogee and perigee. So if anybody's thinking about constructing a flat Earth model, we need to take these cycles into consideration. And believe me, to try and get your head around all them cycles, it's difficult. But again, I repeat it. I'm not going to go through this. Obviously, we've been going 2 hours now, so I'm just going to go through this one quickly. But same observations at apogee and perigee. Yeah, second observation. And again, there you go. Get the same results. So when the moon's at apogee, it appears smaller. And when it's at perigee, it appears bigger. And there's just a quick video here, just showing you the actual change in angular size. Remember, always shot at the same focal length and always shot at my zenith to keep my observations consistent. And there you'll see quite a big difference in perigee. I'm only measuring the radius from the top to the bottom. I'm not measuring anything else, just the radius. Yeah. I always measure the radius from the same points on the moon. You know what I mean? That's why sometimes the angle's at a different angle, because the moon's at a slightly different angle, but I'm always using the same points. So, we can say that the anomalistic cycle, there is a cycle, you know what I mean, and it is measurable. So there is a point of apogee and there is a point of perigee. I'm not saying that the ridiculous distances in the globe model, but there is a change in angular size in the moon between apogee and perigee. So here are a few cycles just to try and get your head around. So you've got the anomalistic cycle, which is based on the eccentricity of the moon, or the closest point or the furthest point, which has got a cycle of 27.55 days. The sidereal, the time it takes the moon to pass through all the constellations and reach the same point in space, is 27.32 days. The tropical cycle, the time it takes the moon to get from the Tropic of Cancer to the Tropic of Capricorn and back to the Tropic of Cancer, is 27.32 days, very similar to the sidereal. The draconic cycle, or the nautical cycle, is related to eclipses. Now, eclipses, you've got 2 points of alignment called nodes, and the time it takes the moon to get from one node to the ascending node back to the descending node is 27.2 days. And the synodic cycle, which is the phases, the time it takes the moon to pass from new moon to new moon is 29.5 days. So there's a hell of a lot of cycles to get your head around. And what I'm doing, I'm testing a lot of these cycles. When I test the moon at zenith, what I'm doing, I'm building up observations of the moon at different points on the tropical cycle. So eventually I'm going to be able to present the tropical cycle and obviously measure the tropical cycle. I've measured the anomalistic cycle. Yeah. The moon phases, obviously you just need to catch the moon through every phase and time it. And obviously it should be 29.5 days. That does change slightly. There is a slight variation in that. But as you can see, there's quite a lot of the moon cycles to get your head around. Now, interestingly, on the night of the July 2018 eclipse, something very interesting happened. Because the moon was at its furthest point at apogee. Yeah? So the anomalistic cycle lined up. It was at this furthest point on the Tropic of Capricorn. Yep. So the tropical cycle lined up. The moon was also, it was an eclipse. So obviously the nodes lined it up for an eclipse. And also it was a full moon. So the phases lined up. So every single one of them cycles lined up. Every single cycle lined up. And what we got was a lunar eclipse. And we didn't only get just any old lunar eclipse. We got one of the longest lunar eclipses we've seen in our lifetimes. Now, my question is the only time you're going to observe a 100.0% full moon is during an eclipse, or very close to an eclipse. If you shoot the moon, a full moon, yeah, when it's not an eclipse, what you'll find is that the moon doesn't actually reach 100%. It actually sometimes reaches 99.9%. Last full moon, yeah, the moon only reached 99.8%. The lunar month before that, it reached 99.9%, and the lunar month before that, when it was the partial eclipse, it reached 100%. Yeah, so you can see there's like a pattern in it as well. Well, basically, during an eclipse, you will see a full 100% moon. Now, I wanted to find out how long this moon remained at 100% full, and that's what I did in this observation. But interestingly, on this shot here, this is actually a screenshot captured on the video I shot, and I caught this black dot. I thought I'd caught my first satellite. I was like, yes, I've actually caught a satellite. But when I actually played the video back, I caught something different. There you go. So the only thing I've ever seen pass by my viewfinder while I've been observing the moon, yeah, is bugs, birds, and anything else what blows in front of it. I've never seen a satellite pass in front of it. They claim there's thousands and thousands of satellites out there. the likelihood is of not seeing a satellite past the moon is very, very slim. So as you can see there, if you look at a lunar eclipse moon, it's 100% full. You can see clearly that it's a full moon. So I wanted to find out how long does that moon remain at full at 100%. Now, if you look at the full moon down here, you can see it's 100.0% according to MoonCalc. Now, based on my observations over the last 3 years, we can clearly say that MoonCalc's accurate. If anybody, it's me who's not accurate. If I'm a degree out, it's probably me, isn't it? You know what I mean? So we know that all my observations match up with MoonCalc in regards to the position of the moon and the declination angle. So we can probably rely on MoonCalc as fairly accurate information or data. Well, Ron Hagman found out some interesting information. The guy who created MoonCalc apparently is a flat earther. And MoonCalc's actually based on a geocentric model anyway, because if you look, you've got a fixed map and you've got the celestial objects that move around the map, you know what I mean? So it is actually based on geocentricity anyway. Well, you can with, obviously, I've just used it for the moon direction and the declination angle, but we can fairly say that MoonCalc's pretty accurate, you know what I mean? You can go 10 years into the future or 10 years into the past and it'll tell you the position of the moon as well, so it is pretty accurate. And a lot of this information is based on Babylonian documentation as well, you know what I mean? Like the Saros cycle. So the moon follows a cycle, and it's an 18 years, 11 days, and 8-hour cycle, and they call it a Saros. And that was documented like in the Babylonian times, 2,500 years ago. That's how the ancient civilizations were able to predict eclipses through the Saros cycle, because the eclipses all follow a cycle. See the eclipse on this night, on the 27th of July, guess what? In 18 years, 11 days, and 8 hours time, guess what? There's going to be an identical eclipse. You know what I mean? That's how they build up the eclipses. Once you've got that pattern, it falls in clockwork as regular as birthdays. Once you've built up that Saros series, you can start on your next series of cycles. But when you've been documenting the moon for hundreds of years, you'll build up a database. You know what I mean? Yeah, so anyway, but what I'm trying to show here is that this actually completely debunks the heliocentric model. And you know Crow X, you've had him on the show a few times, haven't you? Well, he tried to model this in his model, and he completely failed. And when I commented on his model, what he did, he only run his simulation for 5 hours. Yeah? And his model, when he ran his simulation using real data, his model, the moon went from 100% full to 99.8% in 5 hours. He couldn't model it in the heliocentric model using the real math from the heliocentric. Yeah. And I asked him why he stopped at 5 hours. He couldn't give me a proper answer. The reason why I stopped at 5 hours, because if he went any further, it'd be down to 98%. You know what I mean? So what you'll see here, though, is the moon, according to MoonCalc, is at 100% full at 15:45 on the 27th of July. So I wanted to find out how long that moon remained at full. So what I did, I basically run a simulation on MoonCalc, and the moon remained full until the following day at 3:02 the following morning. There you'll see, look. There you'll see, look, full moon, 100.0%. It uses a decimal point as well. So that moon remained full for 11 hours, 22 minutes. That's half a day. That is absolutely impossible to model. Remember, the heliocentric model, the moon is constantly in motion around the globe, yeah, relative to a fixed sun. So I'll give you an example. If we look at it here, look, the sun is relatively fixed, and the moon is supposed to be orbiting the Earth in an elliptical orbit, which we just proved earlier on with Kepler's law, yeah? So at what point could that moon remain full for a half a day? It should remain full for minutes. You know what I mean? So that, yeah. So, I mean, I either the heliocentric model's wrong, or MoonCalc have got all their data completely messed up. The likelihood is their data's correct. Yeah. And the heliocentric model is wrong. And like I say, I was hoping to catch that full moon on the I think the 27th of July, but due to weather conditions and the good old British weather, I couldn't. I wanted to catch the moon when it was obviously full and see how long it actually remains full with real observation. But I had to rely on the data. But as I've shown, it's pretty reliable data because every single one of my observations matches up with their data. So electromagnetism and gravitation. This is taken from a book called Ether and Gravitation by an author called William Hooper, who was an astronomer. Yes, he was a globularist, but one of his quotes in his book was, if either of these forces is to be done away with, it must be the mysterious, intangible, unphilosophic attraction of gravitation, which must be replaced by the philosophic and known attraction of electricity, which can be traced to a physical medium, the electromagnetic ether. So even then, he's claiming that the ether exists. You know what I mean? But based on the Michelson-Morley experiment, they claimed that it doesn't exist because they couldn't detect it through they couldn't detect the motion of the Earth through the ether. So they abolished the ether. But the reason why I showed that is because I want to give my thoughts on what the moon is. There's been a lot of questions regarding the moon. Some people think it's a rock in outer space. You know what I mean? It's 238,000 miles away. Me personally, I think that object we see in the sky is a focal point projection. What that moon is beyond the firmament or in the firmament, and we're just seeing it with our atmosphere acting as a giant lens, and it's basically, we're just seeing that focal point image of the moon. What I did here, I shot the moon with a filter on my camera, and what it did, the white spot is the actual moon, and it created a flare, and it produced an image of the moon. So imagine the moon in the firmament and our atmosphere acting like that giant lens. That's why the moon would apparently appear close, you know what I mean? Yeah. I'm not saying it's a solid object. I'm not saying it's a hologram. But I'm saying the object we see in the sky, yeah, it could be a focal point projection. I'm not 100% sure. But from my observations, I've come to them conclusions, and I'm going to stick to that. So for me, that object we see in the sky, what's lighting up them clouds locally, from my perspective. Now, when the moons are lighting up the clouds for me here, do you think the moon's going to be lighting up the clouds from the same clouds from your location? No, it's going to be lighting up a completely different set of clouds, which exactly. So these are my thoughts. So the electromagnetic ether. They tell us that matter comes in three forms. We've got liquid, solid, and gaseous. It could be. It could well be. Yeah, like I say, I'm going to show you something interesting in a minute, and we'll get to that because I've covered that here. So we know that matter comes in three forms: liquid, solid, and gaseous. But as we know, and probably, there is a fourth form of matter, a substance which is on the verge of being supernatural, a substance which was abolished on the back of the Michelson-Morley experiment, the electromagnetic ether. Basically, it's a luminiferous substance for the propagation of light, and it's in a constant state of motion, and it carries all the heavenly bodies according to their varying altitudes, frequencies, and distances. And it's made up of two great vortices. So you've got one in the north, and this is a recent star trail I captured with my new Nikon Coolpix P1000, pointing my camera towards Polaris. And as you can see, the stars rotate in a counterclockwise direction. And also, we have a vortice in the south, which appears to be rotating in a clockwise direction. Well, you are facing south when you shoot that one, and you are facing north when you shoot the other one. But when you put them together, what you'll see is one rotates one direction, one rotates the other direction. So my thoughts on that were the sky is made up of two circuits. you've got a northern celestial pole and a southern celestial pole. Now, I'm not talking geographic poles on a globe. I'm talking poles like on a magnetic field. So when the moon appears to be circling the northern circuit, as it gets southern declination, crosses the celestial equator and picks up on those ethereal currents in the southern circuit, it appears to be circling in the southern circuit. A little bit like this time lapse here. And as it gets northern declination, it goes from appearing to be circling the southern circuit, picks up on the ethereal currents in the northern circuit, and it looks like, or from our perspective, appears to be circling the northern circuit. So if you look at, this is a time lapse when the moon is in the northern circuit, and as you can see, it follows the stars, so it appears to be circling that northern circuit. The center is towards that way. That's an observation which was made by Genefredo, and also obviously should really mention Genefredo for the zoom across Lake Ontario to the Toronto skyline. That from Jenna as well. Also, if you look at the moon when it's shot on the celestial equator, yeah, it appears to travel in a pretty straight line. I captured that one myself on the summer solstice this year. And also, if you look at the moon when it's on the Tropic of Capricorn, it appears to be circling the southern circuit. As you can see, that is the northern circuit now, that side, and this is the southern circuit, and the moon is following the stars. If you look at a time lapse from the equator, what you'll see is you can actually see both celestial poles from the equator. This is obviously an animated time lapse, smack bang on the equator from a high altitude, and you can see both celestial poles. You can actually see a shooting star in the southern celestial pole there, which is quite interesting. You know what it looks like to me? It looks like a magnetic field. The sky looks like a giant magnetic field. And if anybody knows anything about a magnetic field is, you have one field rotating one direction and one field rotating in another direction. Just to give you a visual of that, I see the sky as two huge wheels in the sky. So you've got one wheel which appears to rotate in a clockwise motion, and one which appears to rotate in a counterclockwise rotation. So in the northern hemisphere, it rotates that way, and in the southern hemisphere, it rotates that way. It's a little bit like a figure of 8. And if you look at that time lapse, what I showed you from the equator, and you take that image, this image here, and you turn it on its side, they look very uncanny. They look very similar to each other. You know what I mean? There is a resemblance. You've got you just hit the nail on the head. Everything is electric. The sky is electric. We have electrical storms. Yeah, I don't know if you've seen that presentation where he's got the mice, and he's got them in like a little, like a balancing thing. He's got one mouse in one side and one in the other, and he's got a superconducting magnet. And as he approaches the mouse with a magnet, the whole thing starts swiveling round. It's because the mouse creates its own dielectric field, just like a human creates its own electric field. You know what I mean? Everything about us is electric. Yeah. If our heart stops beating, what do they do to bring us back to life? They give us electricity. So what I've done here is, so when the moon is high on the Tropic of Cancer, it appears to be circling the northern circuit. And if you go to 70 degrees north, what you'll find is that the moon is circumpolar. If you look there, look, the moon never sets. It's visible 24 hours a day. But at that same time, yeah, all right, this can't be verified, but if you go to 70 degrees south, the moon's not visible then. 2 weeks prior to that, though, guess what? The moon's visible in Antarctica for 24 hours. And at that same time, in the northern hemisphere, 70 degrees, it's not visible. That's because the moon is circling the southern circuit, and as it gets declination, it'll be circling the northern circuit. That's just, and I call it the lunar lemma. So if you look at the moon over a 2-week period, it seems to draw that figure of 8 shape. We're seeing this quite a lot, you know what I mean? We're seeing that shape quite a lot now. And if you look at the ancient cosmology and you look up the ether, what you'll see a lot is depicted by a snake eating itself. Yeah, is it uncanny that the ether or the free energy sign is depicted in ancient times by a snake? And guess what? You got that figure of 8 again. So for me, the sky is just like a giant figure of 8, and then the moon passes from one circuit to the next circuit. We're nearly at the end now, thank God. It's been a quite a long one, this, hasn't it? Maybe I need to. So, what is the moon? You know what I mean? We've been observing the moon for thousands of years, yeah, and it's there nearly every night, and we still don't know what the moon is. Now, based on a few of my observations, yeah, sometimes the moon looks like a light. Many times it just looks like a light in the sky. It could be a light in the sky. Sometimes it looks like a rock. You know what I mean? Many times we look at the moon and think, wow, it looks like a rock. Sometimes it looks spherical. If you look at the moon shot here, it looks a little bit like a ball. But then again, you look at it another time, it looks like a disc. It looks like so many things. It looks like a projection. It looks like a hologram. Remember the image I showed you before? Looks like it emits light. Yeah, it looks like the light's actually coming from the moon. And then again, if you look closely up with the P1000, see these shadows here, it looks like the moon's reflecting light. You know what I mean? From a light source. So the word month is actually derived from the word moon. Yeah? And the word lunatic is actually derived from the word lunar. There's a lunatic there, look, doing some street activism in Liverpool. Oh, it's me. So, like I say, we've observed the moon for like thousands of years, yeah, and we still don't know what it is. We could observe the moon for another 1,000 years, and we'd still be none wiser. Yeah, but one thing I know the moon is not, and it's not that. You could probably remember this from my previous presentation. I think it's a good point to finish on the moon. You know what I mean? This is what they claim is a real photograph from 1 million miles away from the epic Discover satellite. Clearly, it's a cartoon. I mean, I'm not being funny, but every single image I've took of the moon is better than what they can produce. Yeah. And by the way, Elon, we have a problem, because if you look at the Earth, they're nearly the same size. Well, in Mexico, it'll be on the Tropic of Capricorn in Mexico, when it's high on the Tropic of Capricorn. Yeah. So just to finish this off anyway, basically, why do I do all this? I don't do it for profit. I've never made 1 pence out of flat Earth. In fact, flat Earth has cost me thousands and thousands and thousands of pounds. You know what I mean? When I went to New Zealand, I paid for myself. When I went to America, to Denver, I paid for myself. I paid for myself to go to the UK convention this year. You know what I mean? I'm going to Santiago, Chile next year to do a presentation. I'm going to be paying myself. So why do I do it? Because I don't do it for profit. I just do it because I want to know the truth. Yeah. And if I can find one piece of that puzzle, then I'll be happy, and hopefully I can wake up a few people on my journey. Because, like I say, I'm not in it for the profit. I don't sacrifice all my spare time, you know what I mean, jeopardize relationships, you know, all these kind of things, what's happened to me over the few years. I don't do this just for the fun of it, you know what I mean? I do it because I'm driven by the truth. Yeah, talking of lunar buggies, this is from the Apollo 16. Now, when you look at this closely, yeah, this is the remastered version. I just zoomed in a little bit closer. What you'll see is It's a remote control car with a doll driving it. Look, there's just it's unbelievable. No movement at all on the actual astronaut. Anyway, that's it. That's my presentation.
Thank you so much, because I know it's probably cost you things, hasn't it, by doing all the research you've done. I mean, like you said, your life's totally changed.
I was going to say I was actually shouting because I've got the music full blast or the actual sound to all the presentation in my ears, you see. So if I come across I was shouting, it's because I was trying to talk over my own sound in my head, if you know what I mean, because I hear all the sounds. If you put the presentation out there, what I'll do, I'll go back and I'll overlay the full presentation on top of the actual sound, so you can see the full presentation on top of my voice with the actual sounds in there, you know what I mean, like I did last time.
So, you know, as a friend, very much, and you're not a particularly, you're not a very egotistical person about it. That's another thing I like, and the fact that, you know, like we just watched you grow, and, you know, you started off as someone talking about the moon, and now people obviously coming to you and want you to do presentations because of the amount of effort that you've spent looking at the moon. So, you know, as a friend, very much. It is strange, this thing that, you know, looking through, because I know there's a lot of talk about, you know, like when you turn around with the camera, but, you know, I see stars coming from the east, which sort of go across they're sort of going east, and then they sort of go north. I've got stars which go north to south. I've got stars which go east to west. They're doing all sorts of different things, depending on which way you look.
Yeah, and it was good to see Paul on the plane using my presentation in the European Convention. You know what I mean? He took some of my observations, which is what I'm there, which is why I do it. You know what I mean? I want people to, like, you know what I mean? I've used a lot of Jenna Fredo's observations for my presentations. You know what I mean? Which I'm appreciative of, and I hope people use my information and my data, because all my information, all my data is free. Yeah, I don't care if you credit me or not. It's there for everybody to use. If anybody wants anything measuring, send me the images. I'll measure them for free. If anybody wants anything, any observations, any moon sinks or anything, I'll do it all for free. You know what I mean? Yeah, it's there is a lot. I need to do some more research in that. There's, like I say, we've just literally scratched the surface, haven't we? You know what I mean? Like I say, I learn as I go. You know what I mean? Everything I've done is what I've learned over the last few years. I just literally learn as I go. Yes, I've made a lot of mistakes in the past, and hopefully with that moon rotation section in the presentation, you know what I mean? I admitted to making to my moon roll perspective video. I dropped a clanger basically, but I'll put my hands up and say, you know what? I got it wrong.
Okay then, thank you so much for that. So for the recording, we'll say goodbye to everybody, but we'll say goodbye to each other afterwards, okay? Because I hate it when people lob off. I've spent all this time talking to them, and I don't even get to say goodbye properly. But for the recording, mwah, thank you very much, Dave. Thank you very much for spending that time.
It's been a blast.
We lost Patricia somewhere along the line. She was having computer problems. Anyway, mwah to Patricia. But thank you, Dave, and we'll talk in a minute. But everybody, thank you so much for watching. Dave's full of masses of information. I'm sure if you leave comments on the post, he will reply. Anyway, much love, Dave. Thank you very much.
Thank you. Bye-bye. I'm not logging.